So our last chapter, chapter 10, deals with primarily exponential and logarithmic equations. We got to cover some basic introductory stuff before we really get into the meat of that information. Starting with the algebra of functions as well as composition of functions. We can do with functions the same thing we've been doing with expressions for a long time now. We can add them, we can subtract them, we can multiply them, we can divide them. When we do operations with functions, it's called a closed system, which means whenever we add two functions, we always get a new function. It will still be a function. Whenever we subtract two functions, it will still be a function. We'll get a new one. Whenever we multiply them, we get a new function. Whenever we divide them, we get a new function. Okay? The only thing is, when we're doing division, we just can't divide by 0. Okay? But outside of that, we will always get a new function. Okay? And it will retain a function. There's also some properties of both functions that will be inherited by the new function. Things like domain and range are inherited by the two functions that are being added and then applied to the new function. So when we're performing our operations, something that's really helpful to start is to kind of split the functions. I'm sure I should emphasize this part. All right. So our 4 operations, sum, difference, product, and quotient, the notation will kind of vary a little bit. When we're adding two functions, you'll often see it written as f plus g of x. That's how we read that function. F plus g of x. And that means that we're going to take our function f of x and we're going to add it to our function g of x. Same thing with f minus g of x. We're going to take f of x and we're going to subtract g of x. Multiplication can be written a couple different ways. With the multiplication dot or without the multiplication dot. F times g of x just means f of x times g of x. And then this needs a big old parentheses around it. Just didn't look right on the equation editor. F divided by g of x as a fraction. We have f of x divided by g of x. So when we see our different combinations, it's usually helpful to rewrite it as separate functions, just to help visualize when we're doing the replacement and the substitution with the function, and then we go through the process of simplifying. So we're going to start with 3 different functions here. And our functions can have any letters. Okay, I have h of x, g of x, f of x here. The functions can be anything. It could be, a lot of times for profit in business, we'll have p of x. We dealt with projectile motion, height over time, h of t. Okay, these are all functions, so we can use any letters for them. F of x is just kind of the default. Okay, but we can use any letters to represent the function. So, f of x is 4x plus 3, g of x is x squared, and h of x is 2x minus 3. So we want to start with f plus g of x. It means we're going to take f of x, and we're going to add g of x. Okay, well, what is f of x? 4x plus 3. So we replace f of x with 4x plus 3. What's g of x? X squared. So we replace g of x with x squared. So we're adding the two functions together, just like we would add two expressions together. Then we look to see, can we simplify? Can we combine like terms? Can we rewrite it in standard form? Anything that we would do with normal expressions. Okay, we want to try and simplify them. All those properties of algebra are still the same. Associative property, commutative property, distributive property. They all apply to functions as well. Okay? So, do I have any like terms that I can combine? No. Can I rewrite it in standard form? Yes. Yeah. So we're going to say, all right, we've got f plus g of x equals, what's it going to be in standard form? There we go. So when we add f and g of x together, we get x squared plus 4x plus 3. Okay. Part B, same idea, but now we're subtracting. We're going to take f of x, and we're going to subtract g of x. F of x and g of x are the same. Still, they haven't changed. But our combination is going to be what instead? Oh, be careful. Negative x squared plus 4x plus 3. Now, let's have a little thought experiment real quick. What if instead it was g minus f of x? What would change? And minus 3. Because the entire function of f is being subtracted. So we have x squared minus our function, g of x minus f of x. We're subtracting every term within inside that function. So we need to make sure that we apply our distributive property so that we end up with the correct signs. Would I get anything different from g plus f of x? No. It's the same. Because addition is commutative. The order of addition doesn't matter. But subtraction is not commutative. The order of subtraction does matter. So we have to be careful. Those properties of algebra still apply. The order that I add doesn't matter, but the order that we subtract does. So f minus g of x is not going to equal g minus f of x. But f plus g of x will always equal g plus f of x. Okay? All right, so now we have c. F of x plus h of x. So what am I adding together? 4x plus 3 plus 2x minus 3. We're going to add f of x to h of x. Okay, do we have any like terms here we can combine? F plus h of x. All right, 4x plus 2x gives me what? 6x, and 3 minus 3 gives me 0. So f plus h of x equals just 6x. Okay, what operation is D? Multiplication. So we have f of x times h of x. Same as before, we have 4x plus 3 times 2x minus 3. So now what do? We distribute. So what are we going to get? Okay, 8x squared minus 12x plus 6x minus 9. Okay, any like terms to combine? Very good. 8x squared. Combine negative 12x and 6x to get negative 6x. And we're in x squared minus 6x minus 9. So distributive properties that applies even with combination of functions. All right. What operation is E? Division. Again, there should be parentheses here, but it looked weird. So I forgot to fix it. All right. So we're going to take f of x. What's f of x? F of x divided by g of x. 4x plus 3. What's g of x? Squared. Is there anything that I can simplify there? Nothing we can simplify. So f of g of x, 4x plus 3 over x squared. We have our new function. Combination of functions often used in business, such as for profit, is we usually have a function for revenue, and we subtract the function for cost, and that gives us a new function that models profit. Another operation we have is function composition. Okay, has a lot of applications. We've got some in biology with conversions and different things. Okay. So what I have here is a diagram for temperature conversion. We have multiple different ways to measure temperature. The American system uses degrees Fahrenheit. European system uses degrees Celsius. There's also a very scientific measure of temperature, degrees Kelvin, which is a temperature scale that goes from zero movement to just absolutely going nuts as far as heat goes. And we can convert between temperature scales. We have a function f of x equals 5/9 times x minus 32, and that will take any temperature in degrees Fahrenheit and convert it into degrees Celsius. Okay? So I could take, say, 50 degrees Fahrenheit, I could plug it into my formula, 50 minus 32 gives me 18, multiplied by 5/9, and then we indicated 10 degrees Celsius. Okay? So we can convert from Fahrenheit to Celsius. I can then take that same 10 degrees Celsius and I can plug it into a new formula that then converts the 10 degrees Celsius into degrees Kelvin by adding 273.15. And so I get 283.15 degrees Kelvin. So I started with 50 degrees Fahrenheit. I converted the Fahrenheit into Celsius, and then I converted the Celsius into Kelvin. Okay. What function composition allows us to do is skip that middle part. And allows us to write a new formula that goes directly from the original input, in this case Fahrenheit, and gives us our final output, in this case degrees Kelvin. Okay? And it does a direct conversion from Fahrenheit to Kelvin because it uses one function, the entire function, as the input to the other function. Question? Neither. One function becomes the input into the other function. And so this is our notation right here. Okay? Now, we have that symbol. Okay? This expression is read as f of g of x. F of g of x. Okay? F of g of x. That's how we read that function. Yep, that's exactly what we did. Now this symbol right here looks very similar to what? Multiplication. It is not multiplication. Okay? It is not multiplication, it is composition. G of x becomes the input into f of x. We could also flip it around. We could do a different composition. I could say instead of having g be the input, I could have f be the input. And I could have g of f of x, which gives me that f of x is the input into g of x. And so by doing this composition, it allows us to make a new formula that skips that middle step and allows us to get to the final output. So the first thing that I did is I said, okay, if I wanted to take 50 degrees Fahrenheit and convert it to degrees Kelvin, I had to plug in, I had to evaluate f of 50, and that gave me 10 degrees. And then I had to take that 10 degrees and plug it into my function for Kelvin, and that gave me the 283.5 or 0.15 degrees Kelvin. So I had to evaluate both of those functions separately, one at a time in series, and I used the output from my first function to go into my second function and then evaluated it from there. The other thing we can do is just write a whole new function. So instead of doing it through a two-step process, instead of substituting 10 into our function, because then I have to keep doing that. Every time I try to convert, I have to do that whole process again and again and again and again. And I have to solve two equations every time I'm trying to do a conversion. So instead what we can do is say, okay, well I know that f of x is going to be my input into g of x. Alright? F of x is going to be my input into g of x. We can compose the functions and say, alright, let me give myself a little more room. I know that I'm going to take g of x and I'm going to input f of x. I'm going to do a composition where f of x is my input, because whatever I get from that goes into the next function. And so I take the entirety, erase that, go away, thank you, okay. I take the entirety of the expression that is f of x and I replace it into g of x. So the variables in my other function get replaced by the first function. And so that x gets replaced with 5/9 x minus 32. And then we continue with the rest of g of x. So the x in g of x was replaced with the entire function f of x. And then we can simplify this expression. We can apply our distributive property. We get 5/9 x minus 160 over 9 plus 273.15. And then we can combine like terms. We've got our fraction with our decimal. We'll have to round because negative 160 over 9 is a non-repeating decimal. But we end up with 5/9 x plus 255 point, I think it's 37. Someone wants to check me on my math on that. So I completely, okay. So we can take this composition and we can expand it, and then we get a new function that converts directly from Fahrenheit to kelvins. I can put in degrees Fahrenheit into that formula and it will pop out temperature in Kelvin without having to do that middle step. That's what function composition does. And so we can look at it from two sides. We can evaluate it step by step, or we can do the composition and then evaluate it as part of one equation. And so we're going to kind of look at both of those situations here. I've got f of x and I've got g of x. I've got two problems where I'm evaluating for f of g of 2 and I'm evaluating for g of f of 2. And then I've got the same composition, but instead of solving for a value, we just have the variable, which is just going to give us the equation. Okay, and so we're going to kind of look and see how both of those fit together. Erase. All right? So we start with f of g of 2. And what this says is, okay, well, let's take g of 2. G of 2 is going to be the input into f. We need to figure out what g of 2 is. Well, how do I take g of x and solve for g of 2? Plug in 2. 2 squared plus 1 equals what? 5. Now 5 is g of 2. G of 2 is our input into f. So what we're doing now is we're going to take this 5 and we're going to replace g of 2 with 5 and solve for f of 5. That output becomes the input into the next cycle. And so then how do I evaluate f of 5? Plug in 5 into f of x. 2 times 5 minus 5 equals 5. Okay? So then that means that f of g of 2 equals 5. We solved g of x, we took that output, and we plugged it into f of x, we solved that, and then we get our final output. Now let's switch the order of the composition. Now f is the input into g. So which do we need to evaluate first? F of 2 or g of 2? We need to evaluate f of 2 first. So we take f of 2, we plug it in, and what does that equal? -1. What are we going to do with that negative 1? Plug it into g of x. We're going to plug it into g of x. So we take g of negative 1. So we plug in negative 1 squared plus 1 equals what? 2. So g of f of 2 does not equal f of g of 2. They give us two different answers. Composition is not commutative. The order in which we apply the composition will matter and give us different answers. Except for a very, very special case, which we will discuss on Monday. So we did like we did with our original temperature conversion. We evaluated the first function, took the output, plugged it in, and solved. We got our final output. C and D are what we did when we composed one function into the other and just simplified the function to get one function that does the whole thing in one step. So we take f of g of x. G of x is our input. So we take g of x, which is x squared plus 1, and we plug it into our other function. The other way that we can look at this is I have f of g of x is x squared plus 1. I'm plugging x squared plus 1 into my function to replace x. I'm not adding it to x, I'm not multiplying by x, I'm not dividing by x, I'm not subtracting x. I am replacing x with x squared plus 1. So we have 2 times x squared plus 1 minus 5. Let me make that a little smaller because I'm going to run out of room. And then we go to simplify. What's the first step to simplify? Plus 2 minus 5, which equals 2x squared minus 3. So f of g of x equals 2x squared minus 3. Let's compare that to the first problem we did, where we took f of g of 2, we plugged in 2 to g, then we took that output and we plugged that into f. If we evaluate f of g of 2, and I know that f of g of x is 2x squared minus 3, if we evaluate for f of g of 2, it should be the same, right? Well, what's 2 squared? Times 2. Minus 3. Is that the same answer we got the first time? Yeah. So it'll end up giving us the same answer whether we evaluate it step by step or we compose the function and evaluate it all in one go. We're creating a direct conversion from g of x into f of x, evaluating that in one go instead of two. All right, g of f of x. What's my input function for this? F of x is considered the input, right? So we have g of f of x. Okay, so we have g of, what is f of x? 2x minus 5. We have 2x minus 5. So we're going to take 2x minus 5 and plug it in for x. What expression do you think we'll get as a result? 2x minus 5 squared plus 1. Yes, ma'am. Can you wait about 7 minutes? If it's an emergency, go, but it'll take about 7 minutes to finish. All right? So now I need to expand that. 2x minus 5 squared plus 1 gives me 4x squared minus 20x plus 25 plus 1, which gives me a final composition of 4x squared minus 20x plus 26. And just like we did comparing C to A, if I plug in 2 into g of f of x, where I have composed, I will get the same output of 2 that I get from example B. There's a lot of times where you'll have problems that say, okay, you need to compose the functions, you need to do the composition, and then it'll ask you to evaluate some questions after that. There's no point in going backwards to this and evaluating it step by step. As long as your composition is good, just plug in your value to your composition and you'll get the same result. That's the whole point of that composition, is it skips that middle step and allows us to evaluate multiple things under those compositions. The last thing we're going to do is look at building or looking at how compositions are put together and identify what those compositions are. So we have 3 functions. We have f of x, we have g of x, and we have h of x. Okay, those 3 functions. And for the following 2 functions, what we want to do is identify and write it as the composition of either f of x, g of x, and h of x. So we have a new function, big F of x equals the square root of x minus 4. Which of these 3 functions do we need to compose in order to get our new f of x? G of x and h of x, right? These 2 together compose to give us f of x. But we need to compose them in the right order. Which function will be the input to the other function? Which one? Okay, let's try it. You want g of x to be the input, right? Into h of x. Okay, so g of x is x minus 4. We take x minus 4, we plug it into h of x, so we get the square root of x minus 4. So we can see that g of x is our input, so we can just write it as the composition. Big F of x equals h of g of x. G is our input into h. What about for big G of x? Which 2 functions are we going to use to compose? X and g of x. And which one is going to be our input? Okay, let's try it out. You want g of x to be the input? Okay. So g of x is x minus 4. So when we compose, we take 7 times x minus 4, which equals what? Is that the same one? Nope, so let's try it the other way. Let's compose.
If you try the other way, is it possible, or is it always going to be one or the other?
In this type of situation, it should be one or the other, right? Not trying to trick you. Yeah. Now I'm saying, hey, some of these functions I can combine to get my other function. Which one is it? So I've got g of 7x. G is x minus 4. So when we compose it in, we get 7x minus 4. Does that match up? Yeah. So we know that big G of x will equal g of f of x. Yes. G of f of x. X. That's what you're going to do. Okay? Questions, comments, concerns, queries, conundrums?